Okay. Hello everyone. My name is Michael, and I'm going to be hosting today's recitation section, basically covering kind of like the basics of machine learning for those of you who haven't seen it before. Um, to kind of give you an overview of kind of what these recitation sections will kind of cover, essentially, I've noticed that we're going to be focusing a lot about kind of like the technical components of different machine learning algorithms and how they might be applied to healthcare in class. And basically, what I'm hoping to do is kind of supplement some of that material, which with some relevant topics that I think are both interesting and pertinent for your guys' future careers at the intersection of healthcare and technology. And so essentially these recitation kind of modules will kind of compose like a very short kind of mini course on kind of like the basic principles of machine learning, and also kind of their like opportunities and also challenges as they're kind of relevant for healthcare applications. Okay. And so the QR code up here, if you guys are interested, basically this kind of like short course that, I put together, is also available on the internet and also, as a series of web modules and also PDF form, if you guys learn better that way. So yeah, today we'll be doing like a quick overview of like machine learning for those of you who, may have never seen that topic before. Okay, so again, a little bit about myself. So I'm a current fourth year MD PhD candidate. So I completed 2 years of med school, and now I'm entering my second year of my PhD. I'm co-advised by Osbert Bastani in the CIS department and James G in radiology. And broadly, the types of problems that I'm interested in is regarding the problem of distribution shift, right? So the idea that we might have trained machine learning algorithms on one patient population, and we're interested in adapting those types of models to other patient populations. But you can imagine kind of the core methodology can be, widely adapted to many different domains, right? Things like, robotic learning, patient care, and also, drug discovery, medical imaging. And so what that means is that although my research is, kind of very dry lab focused, and I do a lot of, computer science research, it's afforded me the opportunity to work with, many different, professors, students, faculty across Penn's campus, spanning a wide variety of different domains, which is something I really enjoy. So this is again kind of the first of five, five-ish modules for this, these recitation sections. And basically the goal is, kind of distilling kind of these foundational papers and research over the past, couple of decades. And essentially what we've done is we've worked with kind of experts from across, Penn, CIS, the engineering school, and also the medical school to kind of distill all of this into information on what things are most pertinent for, medical students and graduate students and undergraduate students to know about these things and how they might pertain to patient care. And so that's kind of, the whole premise of this course. The learning objectives for this module are, at the end, I hope you can describe what an algorithm is and how they're used, both in clinical medicine and everyday life. Hopefully you can describe what it means to learn and how this concept of learning applies to machine learning. And then hopefully you can identify, potential key applications of ML and when these types of computational tools can be helpful and also potentially harmful, for patients in hospital settings. And this QR code is the same one as the one on the first slide, so there's nothing new here. Okay, so first off, before we even talk about, machine learning, right? I think it's worth just diving into, like what is fundamentally an algorithm, right? I myself, I learn best by example, so I'm just gonna, I think it's best just to look at some examples of algorithms that we might have seen before, right? So this one, if you guys remember maybe from chemistry, right? These represent, the serum concentration of sodium, chloride, and bicarbonate. And so, in clinical medicine, this is a very common algorithm for calculating something called the anion gap, right? Which is used for, downstream, decision making in clinical medicine. But the point is that we take three different, lab values, right? Sodium, chloride, and bicarb, and we compute this, this some other metric called this anion gap, right, that we use in, some other applications that are not super important, right? This one, again, I don't really expect you guys to have seen this before, but this is something called the mean arterial pressure, right, or MAP, which is essentially like a weighted average of your diastolic blood pressure and your systolic blood pressure. So, again, these two measurements, SBP and DBP, they're like your, 120 over 80. So your 120 is your systolic, your 80 is your diastolic, right? And the point is that, again, we take two known inputs and we do some fancy computation. In this case, it's just a weighted sum to compute this other output called a mean arterial pressure, right? This one's a little bit maybe kind of not as familiar, right? And it looks a little bit different from the other two, right? So you guys are welcome to pause the video and kind of read through this. But essentially, just to kind of walk through it, right? This is essentially taken from um, the ICU manual, so the intensive care unit manual at one of the hospitals up in Boston, that is essentially given to physicians and residents in the Boston healthcare system on how do you manage acutely ill patients. And so this is one of their treatment pathways for one of the clinical presentations, right? But I argue that this is also an example of an algorithm, right? It looks very different than the first two. But this is still an algorithm, right? We have, a patient that, maybe looks like they're acutely ill in some way. And then we follow this, this very deterministic algorithm. First thing that we got to worry about is securing the airway, right? And then making sure that they're hemodynamically stable. So what that means is that, their blood is getting to places that, it's supposed to be going in the body. And then we worry about other things, kind of downstream as well, right? And so given an input, patient presentation, we want to do these, deterministic outputs, right? And so these are kind of all examples of algorithms, right? Now, probably the first two you can say, oh, I can pull up these inputs, right, from the patient chart, the health record or whatever, right? And I can compute these, very easily using, numbers and computers and all that stuff, right? This one's a little bit harder though, right? So for doctors, right, doctors are trained through many years of medical school and residency and all that stuff, right? To have these algorithms encoded in their brains, right? But writing this algorithm down in a way that, is easy for other people and for machines to understand, is maybe not so obvious. And so that's kind of the motivation for kind of the rest of this talk. Oh, and yeah, so the actual algorithm is for the treatment of basically, kind of like massive blood clots for acutely ill patients. Okay, so we saw an example of what I like to call a hard to write down algorithm, right? So something that we can kind of describe and maybe understand why it's important, and maybe we even know how to work through it. But it's not really easily expressible on paper, right? And in most like definitely a language that computers can understand. And so, how do we actually learn to write down hard to write down algorithms, right? So again, kind of following our standard example of like looking at how we typically do it in our everyday lives, just as like human beings, right? And so just to look at a couple of examples, right? Maybe in this first example, right, we're given a very, very large data set of genomic data, from our, professor or something, right? And we're asked, hey, just figure out any insights that you're able to get from this data set of human genomes. And so maybe you take the first two principal components, you make a plot, and maybe you see, oh, these people are distributed in this area of the plot, and these other people are distributed in this other place, right? And so one way that we basically learn these types of hard algorithms, right, is that we just look at a bunch of data and see, can we kind of glean any insights from these data sets, right? Maybe another way is, we have many, many, in this case, labeled data sets and instances of, in this case, laparoscopic cholecystectomies, which basically means it's a special type of surgery that, removes your gallbladder. And we have a lot of these, kind of labeled data sets that label, okay, so in this video, frame, this is the liver and this is the gallbladder and this is, the aorta, which you definitely should not cut, right? And so using this labeled data set, maybe we can learn to map, image data to, organs, for instance, right? and just again see kind of many examples of these images, these video frames to learn this, right? And kind of as a side note, there's a surgeon computer scientist here, Dan Hashimoto, who I think you'll hear from later this term, who's kind of doing research exactly in this field. And maybe another component that maybe another example, right, that we've actually kind of talked a little bit about in class is this idea of this artificial pancreas, right? Where we have like a glucose sensor and we also have a insulin pump, and we learn kind of a way to control this algorithm of how much insulin to inject given this particular glucose measurement and history of glucose measurements. And we learn this control algorithm through just experimenting with potentially different options and kind of learning what we call a policy to be able to, optimize some reward function over, the different, actions of, how much insulin you give, right? So, all of these are kind of examples of, kind of learning how do we control, insulin flow? How do we just learn anything, right? And all of these are kind of like data-driven methods. And so you might, for those of you with some machine learning background, you might recognize these as, kind of unsupervised learning, supervised learning, reinforcement learning. And so these just kind of give examples that, maybe instead of trying to look for like a deterministic equation to kind of like express these algorithms, we can instead kind of learn these algorithms, kind of just from looking at a lot of examples of their usage, right? In other words, this is kind of like learning through observation, right? Every new observation that you make, kind of, is a small update to your prior beliefs. So maybe you thought before, oh, injecting a lot of insulin when the patient is hypoglycemic, right? Which means they have low blood sugars. Oh, maybe that's a good idea. And then you learn, oh, that actually leads to really bad patient outcomes. And so you make the update so that next time you see kind of really low blood sugars, you kind of know better not to inject a large amount of insulin, right? So each of these observations that you see through interacting with either past data or with the environment, kind of makes a small update to your set of prior beliefs, right? So the next kind of question that at least I ask myself, right, is that what makes this process different from memorization, right? Um, if I just look at a bunch of examples and I have perfect memory and I'm able to just memorize everything, what distinguishes that memorization process from learning, right? So there are a lot of different answers to this question, but kind of the main one that I want to focus on is in this kind of module at least. Learning basically equates to generalization. That's what it means to learn as opposed to memorize something, right? So after observing many different, data sets or patient outcomes or, glucose measurements or whatever, right? The goal is that, or the hope is that eventually you'll see something entirely new. You'll see something that, a patient that you've never seen before, a data point that you've never seen before, and you're able to generalize so that your algorithm still works pretty well on these new patients, these new data sets, and that you know what to do in the future with it, right? So this is kind of the whole point of learning, machine learning or human learning or whatever, right? Is not to be able to perform well on things that we've already seen, right? It's to be able to generalize, to be able to do things well for things that we haven't even seen before, right? So that's kind of the whole crux of machine learning, right? So kind of to summarize, right, we're trying to, kind of use, data-driven methods, use large amounts of data or the ability to acquire data through interacting with the environment, to be able to kind of gradually update our belief system and our prior knowledge, right? To be able to learn something so that we're able to better and better approximate these data distributions from real life, right? So that's kind of like the essence of machine learning from a very non-technical standpoint, right? The next question that I think everyone should always ask themselves as they're considering like, oh, should I throw ML at this, problem, especially as you guys are thinking about final projects and things like that, right? And so for this, I also want to walk through a couple of examples, right? Right. So as we kind of scroll through these, I want you to be thinking about, should I use machine learning to solve or to answer this question, right? And I encourage you to kind of, as I read it, you can pause the video and kind of think about it for yourself, and then we'll kind of go over the answers. Right? Okay, so the first one is given, patient lab values and chart data, maybe it's extracted from health record data or something, right? predict the age of the patient. Okay. Um, so for this one, the answer is, at least I personally think you should not use machine learning, right? So the reason behind that is that the age of the patient is something that's super easy to already see, right? Like there's nothing that's hard to be able to like compute the age of the patient. You can just ask them. It's very easy, readily available. It's available in the health record data. It's super easy to find, right? So even if you were able to train a model with 100% accuracy on this, this is not a useful model, right? Okay, number two, right? So given patient systolic and diastolic blood pressure data, right, we want to predict the mean arterial pressure. So remember, the mean arterial pressure is the weighted, sum or the weighted average of the SBP and DBP, right? So in this one, I also argue that no, we should not use ML, right? And the reason why is that we already have an algorithm for this, right? We wrote down that the mean arterial pressure is, this weighted average of the systolic and diastolic blood pressures. So there's no reason to learn, the mean arterial pressure using some complicated neural net, when we already have, an algorithm for this, right? And an algorithm that, is literally the definition of this quantity. Okay. Number three, so given patient data, we want to predict their patient's risk of having Huntington's disease. This is I imagine many of you haven't heard of this disease before. So relevant background is Huntington's disease is a very rare genetic condition. It's passed down from, passed down from grandfather, father, and so on and so forth, right? And basically, this is a incurable disease. Once you have it, there's nothing, at least currently with modern medicine, that you can do to cure it or treat it or whatever. It's a slowly progressive disease, and unfortunately, people usually pass away from it. And importantly, there's no cure, right? So for this one, again, I don't think you should use ML for this, right? And this one's a little bit debatable depending on who you ask. But the key thing is that there's no cure, right? There's nothing to do so let's say again, you have a perfect model, perfectly predicts the patient's risk of disease, right? So if the patient has it, you say, okay, you 100% have Huntington's disease. What is the patient going to do with that information? There's nothing actionable that they can do, right, with that information. All they know now is that, oh crap, I have this horrible disease, right? I can't treat it. Maybe like, you can tell family relatives to get checked or whatever, right? But there's nothing actionable clinically that you can do for them. Okay, number four, given a recording of bowel sounds, predict the probability of a small bowel obstruction, which is again just some medical disease, not important what that is. So this one, again, I don't think you should use machine learning. And the reason why is that if you've ever been to the hospital before, right? No one ever records your bowel sounds. This premise that we have recording of bowel sounds, that's like that premise is, false. And so maybe if we start, you know, routinely collecting bowel sounds, okay, maybe this becomes more relevant. But as of now, this is a very, data limited, type of problem to pursue. And finally, okay, so given maybe all of the patient's data, right, genomic, imaging, health record, whatever, right, we want to predict the patient's risk of a very, very rare disease. Right? Um, Again, I think this is kind of limited by data availability, right? If you only have one patient in the world that has a particular disease, not only is such a classification model not really helpful, right? Because the prevalence of this disease is so low. But also this is just really hard to train. If you guys have ever heard of like class imbalance, right? You just have so little positive examples in your training data set. This is just a really hard classification problem to pursue, right? Number five, maybe it's a little arguable. Some people will say, yes, you should, you can still use ML for this. There are techniques to kind of overcome this, but just for the point of argument, I'm just going to say no, right? So the point of going through these different examples, right, is, hopefully through going through these examples, right, you've actually learned something, right, to be able to understand, okay, why, when should I or should I not use machine learning, right? And that's kind of the funny part, I guess, about this exercise or whatever. But the main takeaway, right, is that once you use machine learning, ML is useful for hard to write down tasks, right? So things that you can't easily compute, but or computers can't easily compute with lots of data available and also generates actionable predictions, right? These are kind of like, the three-ish, kind of requirements that maybe it isn't sufficient, but is definitely necessary for you to be able to use ML, in my opinion. Okay, so hard to write down tasks, you have a lot of data available, and you can actually generate actionable predictions. That's kind of like the three takeaways. Okay. Some food for thought for you, as well to consider. And again, there's no right answer to these questions, right? Are there tasks in healthcare for which automated methods like, AI and stuff, right, that should never be used for, using. Sorry. So are there tasks in healthcare for which AI should not be used, right? Um, and kind of once you've thought about that, right, does understanding how these automated methods, how AI arrives at their predictions, does that change whether or not they should be used or not? So this kind of explores, is the lack of interpretability, is this idea that AI and ML, there are these like black box models, right, is what we commonly call them. Is that a reason inherently that kind of prevents them from being used for certain healthcare tasks? Right? So again, there's no right answer for either of these two questions. This is just kind of something for you to think about. But common answers, I guess, to number one, right, are things like, at least right now, people usually don't think that, computers and ML and stuff should be able to just autonomously do a surgery, right? We should have a surgeon, on standby at least, at the very least. And a lot of people also think, okay, I don't think I would want to get, mental health care, um, uh, from a computer, right? That feels very artificial and kind of weird, right? So those are just kind of, two potential examples, right? Again, they're up to debate. They're, not right or wrong, right? So and we'll kind of explore one of these, right? So no one's explored should you use, I guess, AI as a surgeon. I think that's a little bit far-fetched right now, at least. But people have explored, can AI tools, right? Things like ChatGPT and other ones that you might have seen, can these be used as mental health resources, right? And so I'm going to kind of present kind of two different papers, and you're welcome to read these if you're interested, that kind of offer kind of related but competing answers to this question, right? So the one on the left, right, Ayers et al., right, was published last year, and basically looked at comparing physician-generated and AI-generated responses to basically questions posed by patients in like a r slash, I think, Ask Dr. AMA or something like that, or Medical AMA or something. So it's basically just some public social media forum, right? And what they found was that kind of maybe a little bit surprising, um, these like, chatbot generated responses, they were often more accurate, more empathetic. People just like them better. Um, and so this kind of argues, hey, maybe that, AI has a lot of medical knowledge and is able to respond to many, common complaints by individuals made, on a Reddit forum at least, right? And so maybe this can be used as a mental health resource, right? Maybe used for triaging to, oh, here are some helpful mental health resources that, are in your area or something, right? Now, the study on the left by Heston was also published recently, and basically it looked at kind of these simulated scenarios of not real patients, but like kind of like synthetic patient answers, patient questions to a large language model, right? And what Heston found was that, a lot of these kind of generative AI models, they're too slow to escalate kind of potentially concerning situations, right? So if someone was, a patient was, kind of experiencing suicidal ideation or something, oftentimes these language models wouldn't be quick enough to say, hey, you should call 911, or, we need to do something about this. They would still try and talk them down and do other things that kind of go against conventional kind of mental health recommendations, I guess. And so this is obviously a big concern as well, right? And so again, this is not, there's no real right or wrong answer here, right? But the point is that, people are kind of exploring these, and they're kind of pros and cons to both. And I encourage you to think about kind of whether you would, kind of seek mental health um, I guess, support from AI models or what that might look like, right? And things like that. As a potential example, we're not going to go through this together because, this is asynchronous. But, there are, people can kind of develop mental health chatbots, right? And we've seen, maybe a couple related examples in class, right? Where we're able to, give a set of system instructions or, even fine-tune models, right? And again, we'll talk about what these things mean in kind of like future models, right? But the point is like we can kind of specify, models like this, like Mistral model, which is just another, company that developed, like a GPT-like model, right? Um, and tell it, hey, you should act as a mental health coach. So that way, if a user or a patient, right, asks mental health GPT a question, they'll kind of hopefully respond as a mental health coach, right? And so I encourage you to kind of play around with this, try and test, a couple questions and see, um, you know, how you like their responses, what are their limitations and things like that. And an important thing that, I hope people recognize is that, the models like these, right? Like this one here, if you click on this link, are hosted on a website called Hugging Face, which is publicly accessible. Like you don't need a Hugging Face account to be able to chat with this bot. And I think that really speaks to, people are still doing research on generative AI and these language models and things like that. But this is a resource that's already being made available for patients, right? Any patient can go on the internet and be able to click on a link like this and actually chat with this bot to potentially actually get mental health advice, right? And so this is not just like some kind of like, research academic exercise on like, how these things, kind of like might impact patients. These can and are, already impacting patients. And it's something that's kind of, we as researchers are, kind of struggling to kind of keep up with, especially with the pace of technological, advancements. Um, but, it's something important to recognize, and I hope you guys take away from this as well. Okay. Kind of as a final note, right? We looked at one example model here, right? So this is again just some other example, right? Mistral, and the other stuff is not important, right? But there are many, many different examples that you guys can play around with, right? So you guys are probably most familiar with like ChatGPT from OpenAI, but a lot of different other companies out there have these really great state-of-the-art models, many of which are open source, meaning that you can play around with if you have like a sophisticated enough, compute setup. And I think one thing that's interesting is that a lot of, I guess, academic institutions like Penn, right, are now exploring, can we instantiate kind of like these language models and stuff like that on their own, proprietary, their own servers kind of behind kind of like their own firewall, right? And so an example of this is that the University of Pennsylvania Health System, UPHS, has this UPHS Copilot model, which I'm not sure if you guys have access to, but essentially it's available for any clinician, anyone with UPHS access, to be able to use these AI models and actually give HIPAA protected information so that the model can use that to, generate recommendations. And if you guys are interested, I'm happy to kind of demo this with you guys, if you guys don't already have access. Okay, so what are the key takeaways that I hope you guys take away from this, right? So the key thing is that number one, algorithms in general are just any function that maps a set of inputs to outputs, right? Inputs being, lab values, medical data, imaging data, whatever, right? Outputs being, certain other lab values, right? Or predictions, classifications, segmentation maps, and some of these things will talk about in future kind of modules and recitations, right? And so some of these algorithms, they're easy to describe and easy to write down, and other ones are a lot harder, right? And so the goal of machine learning is instead of figuring out how can we write down an algorithm explicitly, instead let's just kind of learn this algorithm through seeing many, many examples of past observations and past data, right? And this really mimics how we as humans also learn as well, right? Um, and the goal of, not just machine learning, but any form of learning, right? Any form of discovering new algorithms, is to be able to generalize to new sets of inputs. Okay. And kind of so that's kind of, hopefully kind of a very quick overview of machine learning, right? The next couple of recitation sections will be exploring, what are the opportunities and challenges associated with these types of models, right? So things like how can these models introduce new biases? How can they lead to unequitable outcomes for patients? How can they compromise or protect patient privacy? And this whole notion of algorithmic interpretability, which we like, briefly explored, here today, and other things like that. So with that, I encourage you guys to leave feedback here if you guys want, but it really, it's up to you guys, just so I can improve this. Let me know if there's anything in particular that you guys want to learn about or hear about. But yeah, hope this was helpful.